The process of balancing a half reaction follows a method that I described in an earlier video linked to in the description below and floating over my head somewhere. Step one is look at your initial reaction and identify the oxidation numbers of all of the reactants and products in order to determine which substances get oxidized and which ones get reduced. So let's go ahead and start there, beginning with the easy ones. The easy ones are the atoms that are all by themselves with a charge floating over them, like bromide here. Whenever you have such a situation, its oxidation number is equal to the charge. So it has a -1 charge, so its oxidation number is -1. For manganese, we have a +2 charge, so its oxidation number is +2. And for bromine here, this is Br2. That's a substance that is only bonded to elements of the same substance. So we have two Br atoms bonded to each other with no floating charge indicated up there. So by our oxidation number rules, what is its oxidation number? Yeah, it's 0. So we have all the easy ones down. Now we're going to look at this one. What do we do here? Well, manganese is located in the D block of the periodic table, so identifying its oxidation number or charge is not as straightforward. So what do we have to do? Well, we have to determine manganese's oxidation number by identifying the oxidation number from or deriving it from the oxidation number of the other things for which there are hard, fast set rules. So for oxygen, anytime it's not O2 all by itself or it's not in hydrogen peroxide, according to our oxidation number rules, its oxidation number is -2. So I'm going to just make note of that. I'll point an arrow at oxygen and write -2. Now there are 4 total oxygens in this substance here. So what's the total charge ebbing off of all 4 of those, each one with a -2 combined? In order to do that, I take that -2, and I forgot to put the negative sign there, my apologies, and I multiply it by 4. I have 4 total oxygen atoms, each with a -2 charge. -2 times 4 is going to equal -8. So that is the total charge ebbing off of all 4 of those combined. Now the total leftover charge or net charge of this entire substance as a whole is -1, indicated by that floating charge there. So whatever the oxidation number or charge is of the manganese, it has to be a number such that when added to -8 leaves behind a -1. Does that make sense? So I have to have a number here that when added to -8 leaves behind the net charge that I have up there. What number is that? Yeah, you can see it is +7. And because there's only one manganese contributing to that +7, that is the oxidation number of that manganese. So I'll go ahead and make note of that. Now, armed with our oxidation numbers or states of each substance on the reaction, we're going to identify which one gets oxidized and which one gets reduced. We do that by looking left to right and identifying the substances whose numbers have changed as we go left to right. So on the left, the manganese has a +7, and on the right has a +2. That's a change. So it goes from +7 down to +2. Okay, so what is that? Well, if I start up here at a +7, I get knocked down to +2. I'm getting reduced. In other words, I'm becoming less positive. I'm becoming more negative. And that occurs by gaining electrons. So that is my GR for my mnemonic. Leo, the line says GR. Manganese is the thing that gets reduced. Now, what about oxygen? Well, there's no oxygen over here, is there? Because the reaction isn't balanced. So that's what we're going through this process for. So let's focus on the bromide. -1 on the left, 0 on the right. That's obviously a change. What's happening there? Well, it begins at a negative level and gets knocked up to a 0. So it's becoming less negative, more positive. How do you do that? By losing electrons. Remember, electrons are negatively charged. So if you gain electrons, you become less positive, more negative. If you lose electrons, you become less negative, more positive. So I'm going down here from -1 all the way up to 0. So I'm losing electrons to become less negative. So that is my Leo. In other words, my oxidation reaction is my bromide Br- turning to Br2, and my reduction reaction is my permanganate ion with my manganese +7 being reduced down to +2. So this is the next step of this process. It's to take this information and separate it out into 2 separate reactions, the oxidation reaction and the reduction reaction. These separated reactions, that is, these reactions in which we just focus in on the oxidation and the reduction separately, are called half reactions. The next step in this process then is to balance each of these half reactions, beginning with balancing all of the elements that are not oxygen or hydrogen. So with the oxidation, I've got 1 Br atom on the left, and I have 2 on the right embedded in this subscript. That doesn't balance. So how do I fix it? By adding a 2 coefficient right here next to the bromide. That is now balanced. How about the manganese? Well, balancing all of the atoms that are not oxygen or hydrogen, I have 1 manganese on the left, and I have 1 on the right. So that is balanced. The next step, again, according to principles that I outlaid in an earlier video linked to in the description below, is to balance all the oxygens anywhere where applicable by adding H2O wherever necessary. So over here, you can see there's no oxygens up on this reaction here, but down here in the reduction there are 4 oxygens on the left. So I need to add 4 oxygens on the right by adding H2O. So I'm going to add 4 molecules of H2O. I'm now done with that step. My oxygens are now balanced. You can see that by doing that, though, I added a bunch of H's. So what do I do next? Well, the next step is to add H pluses. That is if you're under acidic conditions, which is what this reaction is specified as in our original question. Acidic conditions. So under basic conditions, the rules are a little bit different. I do talk about that in an earlier video. But under acidic conditions, anywhere that you've added H's or have H's, you balance that by adding H pluses wherever necessary in order to balance out your H count. So I have 4 multiplied by 2 is 8 total H atoms. So I'm going to add 8 H pluses on the left side. Now I've balanced out my H's. We're not done. The next step is to add electrons, E minus, as many as necessary in order to make the charge the same on both sides. For example, in the oxidation, you can see I have a -1 charge, but there's a 2 coefficient. So if I multiply the 2 by a -1, it actually gives me a -2 overall charge on the left side. How do I balance that out? By adding 2 individual electrons on the right side. And that's the way we indicate an electron. I have an E minus with a 2 in front of it. So now my charge, net charge on the left is -2, and on the right is -2. You see that? Now for the reduction, it's going to be a little bit more complicated because what I have on the left is I've got 8 H pluses. That's a positive 8. And I have a -1 charge there. So I take an 8 plus -1, and that leaves me behind a +7 on the left side of the reaction. On the right side of the reaction, I have H2O, which has 0 net charge, and I have a +2 here next to the manganese. So the charge over here on the right is a +2. That doesn't match, does it? So I'm going to have to add electrons somewhere to make sure that they match each other. I can't really, if I add electrons here, I'm going to be shrinking the net charge of the +2. And that's going to take me further away from the +7. So it might be easier and better to add 5 electrons over here to the left. See, if I add 5 electrons, that takes me or gives me a -5 added to the mix. If I take -5 plus 8, -1, it leaves behind me, a +2. And now my charges match. I'm now done with that step. You follow that okay? We've now balanced the half reactions. The next and final step in order to get to the net reaction is to look at the electron count. I've got 2 electrons in the oxidation, 5 electrons, in the reduction reaction here. And I need to multiply each of these by whatever I need to in order to get them to be the same. In other words, 2 times something will give me a number that I can also reach by multiplying 5 by something. What's the easiest way to do that? The easiest way to do that to me is by multiplying the top reaction by 5 and the bottom reaction by 2. You see what I'm saying? If I take that 5 and multiply each coefficient by 5, it'll give me 10 electrons here. If I take a 2 and multiply every coefficient in this reaction by 2, it will give me 10 electrons down here. Those 10 electrons cancel each other out, and I can add all of the left sides of both reactions together to get a net left, and do the same with a net right over here to get the overall final reaction. Now this question does not ask for the overall final total reaction, it just asks for the coefficient, I think, in front of the permanganate, which is the MnO4 minus, once you go through this entire process. Does that make sense? So I'm going to go ahead and multiply everything by 5. So if I take 5 times 2, it turns it into 10, and I'll go ahead, I'm going to get a -10 overall charge on the left now. 5 through here is going to turn that into 5. It was a 1. 5 times 1 is 5. Now I take 5 times 2, and that's going to give me a 10 right there. You'll notice that the overall charge on the right now is also -10, so I'm balanced. Now I'm going to take 2 and multiply it by everything here. 2 times 5 here is 10. 2 times 8 is 16. 2 times an implied 1 is 2. And then I continue going through. 2 times this is 2. 2 times that 4 is 8. Everything should balance, and you'll notice that the charge ends up balancing out to be +4 on the right, as well as -10. See, I've got 10 multiplied by, I got 10 electrons, each with a -1, plus 16, and -2. So you have 2 permanganates, each with a -1. 2 times -1 is -2. If you add all that together, you end up getting, +4 right here, which does indeed match charge-wise. You'll notice again that what we've done is we've achieved having the same number of electrons fed into the reduction equation as we had electrons spit out as a product of the oxidation equation. And the question asked, what is the coefficient once you go through this entire process of the permanganate ion? This one right here. And as you can see, it is 2, which lines up with answer B.